I have a website that, well, Khan Academy has a website where Sal Khan, he explains first and second derivative of parametric functions. And it's about 6 minutes long, so not very long. So if you want to go watch that, he does a nice job of explaining why you have to divide by dx dt in the second derivative. So let's start here. Let's go. Students will be able to find extreme values of parametric functions. Exercise 7 through 16, find A, the first derivative, and B, the second derivative in terms of t. So problem number 8. Letter A, first derivative, dy dx is equal to the derivative of y is negative square root of 3 sine of t, and the derivative of x is negative sine of t. So the signs cancel out, and the first derivative is square root of 3. B, the second derivative over dx2 is equal to the derivative of the first derivative, which is 0, but then you have to divide by dx dt again. The derivative of x is negative sine of t. In this particular problem, if you would not have, you'd end up with the same answer, but that's coincidence. You have to divide by dx dt. Number 10, the first derivative, dy dx is equal to the derivative of y is 1 over t. The derivative of x, well, x is t to the negative 1, so the derivative is negative t to the negative 2. So we have negative 1 over t squared. Now we're going to multiply the top and bottom by t squared. Those cancel out. One of those cancels, and the first derivative is negative t. Letter B, the second derivative is equal to negative 1. That's the derivative of the first derivative, but you have to divide by dx dt. Divide by negative 1 over t squared. Multiply the top and bottom by t squared, and we get, well, t squared. That is the second derivative. A, sketch the curve over the given t intervals indicating the direction in which it is traced, and use a calculator for this. So let's graph this parametric function. Let's go to mode. I guess I was in parametric already. So mode, yeah, I'll show mode. Make sure you're in parametric here. And y equals. We got t squared plus 2t. And then t squared minus 2t plus 3. From negative 2 to 3, let's do this first. Let's go zoom 6. And it doesn't quite fit. So let's change our window to go from negative 2 to 3. And then, I think if I remember right, negative 2 to 20 fit the x's. And then negative 1 to, I think 15 took care of the y's. Let's graph it now. Yeah, that whole graph fits on there now. Now remember, parametric has a beginning and an end. And let's graph it again, we'll pay attention to what direction it's graphed. So we'll slow it down a little bit. Go to, 2 points. Let's go with 0.01 like that. Then graph it. It'll be much slower and kind of going, left to right, kind of. So on part A, we're just going to make a sketch of this. So it's doing something like that, right there. Part B, identify the requested point. The requested point is the leftmost point. And we could use a trace here, and we could trace through the t values. Oh yeah, I changed so that it'd graph a little slower. The original is pi divided by 24. So let's graph that, and now we'll trace. And the leftmost point is about negative 1. Well, it is negative 1/6. It's negative 1/6, and now they want you to show that it's negative 1/6 using calculus. So justify that you have found the requested point by analyzing an appropriate derivative. You may use a grapher. Well, leftmost point means we're minimizing the x value. That'll be the leftmost point. So let's take the derivative of x. So 2t plus 2, and we're going to set that equal to 0. So 2t equals negative 2. I was thinking ahead there. Negative 2 divided by 2 is negative 1. So the t is negative 1. So the point is, we're going to plug t in for the x. the t's and the x, and then we'll plug -1 into the t's for the y to find the point. So when we plug -1 in, we get 1 minus 2, -1. We plug 1 into here, let's see, we get -1 squared is 1, plus 2 plus 3, and we have 6. So there's -1/6. Same instructions. Let's go y equals. We'll clear this out and get tangent of t. That's the x. And then 2, let's go 2 divided by cosine is secant. Whoops, I need a variable in there. There we go. Let's graph this. Oh, and we're only going from -1 to 1. So window -1 to 1 radians. And let's go -2 to 2 on this. And -1 to, I think 3 will be fine on the y's. And graph, oh, not quite. I need a little higher on the y's. So y max, let's go, I think maybe 5 will be okay? Yeah, 5 is fine. So letter A, 1, 2, and it seems to be doing, whoop, I missed a little bit. Seems to be doing something like that. B, the lowest point, seems to be 0, 2. Letter C, if I want the highest or lowest point, we're going to take the derivative of y. So dy dt is equal to 2 secant tangent. And we want 2 secant tangent equal to 0. Well, now let's figure out where tangent is 0. Tangent is 0 at 0. We have the point 1, 0. Tangent is sine over cosine. So t equals 0. Now, the reciprocal of 0 is undefined, so we got to make sure that secant is not undefined where tangent is 0. And secant is the reciprocal of cosine, so we're fine at 0. So reciprocal of 1 is 1. The only other place where tangent is 0 is t equals pi, which is approximately, of course, 3.14, and we're only going to 1 radian, so 3 radians is too far. So there's only one point, 0. So now we need the point. Let's plug 0 in for x. Well, the tangent of 0 is 0, and 0 in for secant, and the reciprocal of cosine at 0, well, cosine's 1, reciprocal of 1 is 1, so 2 times 1 is 2. 2 times 1 there. So 0, 2 is the lowest point. Next, exercise 23 to 26. Find the points at which the tangent line to the curve is horizontal or vertical. Let's graph this. Let's clear these. Oh, by the way, I didn't mention, make sure you're in radians when you graph these trig functions. We have -2 plus 3 cosine, and then 1 plus 3 sine. Now, because both coefficients of sine and cosine are 3, this should be a circle. Zoom 6. There's the circle. Let me capture this. Let's take a screenshot. Send to the current page. Might have to make it, not really. Let's make it a little smaller. Whoops. Whoops. Let's move that over there. Well, we have, what do we want? We have horizontal. Well, horizontal tangent lines are here and here. So there's the horizontal tangent lines. So, and you don't have to do this. I'm going to show you how you have to do this in your homework. But this is more for, just for demonstration. So it looks like -2, 1, 2, 3, 4. -2, 4, and -2, I think it's -2, -2, if I remember right. And that's certainly what it looks like. So the first derivative is equal to, the derivative of 3 sine is 3 cosine of t. And then the derivative of 3 cosine is -3 sine of t. So we have negative cosine of t over sine of t. Now I could turn that into cotangent, but I really don't want to. I want to be able to work with a numerator and a denominator. So for part A, horizontal tangent lines happens where the derivative is 0, where the slope of the tangent line is 0. Now how do we make a fraction 0? We make the top 0. So we want to know where cosine of t is equal to 0. Well, cosine is 0 at pi over 2 and 3 pi over 2. Well, isn't this pi over 2 if this was the unit circle, and then 3 pi over 2 would be down here on the unit circle? But let's find those points using the values that we found. For pi over 2, we're going to plug pi over 2 in for the t's in x and y. So we have the point -2 plus cosine of pi over 2 is 0, and then 1 plus sine of pi over 2 is 1. So we get the point -2, 4. Aha, -2, 4. Now for 3 pi over 2, let's see, we'd have -2 plus 3 cosine of 3 pi over 2 is 0, so times 0. And then 1, and then the sine of 3 pi over 2 is -1, so it's really -3. So we have -2, -2, and those are the horizontal tangent lines. Now, letter B, the vertical tangent lines. We want to know where the denominator is 0, so where sine of t is equal to 0. Well, that's at 0 and pi. So let's plug 0 in for the t's in x's and x and y. 0, cosine of 0 is 1, so -2 plus 3. And sine of 0 is 0, so 1. So that is the point 1, 1 for this right here, over here. So 1, 1. Well, look, that's right here, 1, 1, vertical tangent line. Then I got to plug pi in. Haven't done that yet. Plug pi in. Cosine of pi is -1. So -2 minus 3. And then sine of pi is 0. So 1 plus 3 times 0, really, that's what we have. -5, 1. So 1, 2, 3, 4, 5, 1. Right there, another vertical tangent line. Distance formula. Find the distance from 0 to 3 for x equals t plus 1 and y equals t squared minus 3. So I have it graphed here. The distance. So we want the distance along this curve right here, from these 2 points. What if we were to find the distance between the 2 points using a line? Yeah, I missed a little bit. But the blue, the curve, is going to be longer than this line. But let's use the Pythagorean theorem to find the straight line distance, right? So this side from here to here is 9 units long, and from here to here is 3 units long. So we could say the square root of 81 plus 9. We could approximate the distance of the blue curve by doing the square root of 90. And let's just, for fun, let's get that. Square root of 90. So 9.487-ish. And now you don't have to do this for your homework. We're going to do the calculus, but I just want to explain to you where this is coming from, really. Now, remember that integral is adding up an infinite amount of things. So if we have this curve and we wanted to find the area, we would estimate the area using rectangles. And if you wanted a better estimate, you'd use more rectangles. You want a better estimate, use more than that. So we're going to find the area of an infinite amount of rectangles and make those rectangles infinitely small. And then we end up with this perfect area. Well, we're going to do the same thing here, except with little right triangles and their hypotenuse. So we'll just have a whole bunch of little right triangles, and we'll estimate the curve using the length of their hypotenuse. Well, I could do a whole bunch of a whole bunch of triangles, and that would be a pretty good estimate if I used however many I drew there, 15 or so. But if I wanted a better estimate, I'd have more triangles and more triangles and more triangles and more triangles. Well, to find the hypotenuse, it's the Pythagorean theorem. Now, you would think that, well, we're going to use this is actually, use position to find these values, but really this is the change in y, and this is the change in x. So that's why we're taking the derivative. We want little changes of x and y, little changes of x and y on these little triangles. So we're going to integrate from 0 to 3. We're going from 0 to 3. Square root of, we have to take the derivative of this, which is 1, and we're going to square. There's the dx dt squared, plus derivative of this, which is 2t squared dt. So we need the integral from 0 to 3 of the square root of 1 plus 4t squared dt. And it should be, pretty close to that. We can't do this by hand because we can't make this a perfect square to get rid of the square root. If we could turn it into the square root of 1 plus 4t squared, we'd be good to go. That'd just be 1 plus 4t, and we could integrate that and we'd be fine. So this one is a calculator problem. So math number 9, we're going from 0 to 3, and it's the square root of 1 plus 4t squared. My calculator is still in parametric mode, so it's still doing the t's, dt. Enter, and it is close to that 9.487. It happens to be 9.747, a little bit farther, because we're curving. We're not going in that line, we're curving to get there.